Hi guys, welcome to topic 6.6, naming acids. So we have finally made it to the end of the process of chemical naming. So this is again, like I've mentioned off and on, that chemical naming is not going anywhere, and we're going to spend a little bit of time mixing things together, changing things up to understand where we're at in naming. So looking at this roadmap, we've done everything on the right-hand side. That was topics 6.1 through 6.4. We then worked through 6.5, which is the prefix system, where we have two nonmetals. So then we do the mono, di, tri naming style. So where we're at is this last component of the roadmap here, and that is how to name something that is an acid. So for today's lesson, you definitely need your polyatomic list and you definitely need your periodic table. And so, like we've been doing all along, we're going to work through how to go to a formula and then to go from a formula back to a name. So when naming acids, we kind of have two types. We have binary and oxyacids. And so binary, kind of like the name implies, and we've been using binary before in different compounds that we've named so far, is that it's made out of two elements. And then an oxyacid has three, with the name implying one of them has to be oxygen. So from there, we're going to work through the binary part first. And so I think out of all of them, acids are one of the more difficult parts to name because there are some weird exceptions to the rules, but it's really never explained as to why there are exceptions to the rules. And then we have our different types. And so there's a little bit more going on with acids than what we've seen with our previous naming parts. So when we have an acid, the part that makes something acidic is a hydrogen ion. And so all acids, like it shows here in the naming tree, it asks, is it an acid? Does it start with H? So the one thing we're going to find in common that all hydrogen atoms apply to, or all acids apply to, is that hydrogen is the key component there. And so when we go to the process of naming a binary acid, there's kind of two parts to the name, and the first part is broken down into three parts. So we have a prefix, and this prefix will always be hydro to account for the fact of the hydrogen. We use the root part of the nonmetal, and then we add the suffix ic. So instead of "ide," we're going to use ic. And then the second word is acid. So the best way to learn and understand this is through examples. So I have two examples here. I can see right away that they're binary. The one thing they have in common is that hydrogen's first, so I can recognize that I need to go to the acid branch of my naming system. And then of the types, this is binary because hydrogen and bromine and hydrogen and chlorine. So like I said, to take care of this part of the name and to recognize that this is a binary acid versus an oxyacid, we start with the prefix hydro. The next part is to use the stem, and it's the stem component of your nonmetal that it's combined with. So here we have bromine. So that part is, instead of bromide, we're going to have the bro part. And then our special ending to distinguish that we are now talking about something is an acid, we add ic as our suffix here, not ide. And then the second word is always acid. And again, the acid part corresponds to the hydrogen, the hydrobromic corresponds, or the hydrobromic to the Br. And again, it identifies that this is binary. So in our second example here, we now have chlorine. So the only part that's going to change is this piece here. Everything else, these three pieces will always be in a binary name. So we will have hydro, and instead of brom, it'll be chlor. And then we add our ic and acid. So this is hydrochloric acid. So again, when I go from the reverse direction to a formula, I can see hydro. That's the first red flag. That is binary. I know that my cation is hydrogen because of the word acid. And then my stem here tells me what my anion is going to be. So that's binary acids. Oxyacids are subdivided into two types because there's a little bit more going on because of the polyatomics that are involved, because we're now introducing things with oxygen. So here's two examples of H2SO4 and H2SO3. These are both acids, and so the SO4 we recognize as the sulfate polyatomic and SO3 as the sulfite. And so we have to have a way to distinguish them because they have a different number of oxygen. Therefore, they're going to have some different properties. So we're going to talk about the 8 ions first. So like nitrate, sulfate, those 8 endings. So these change to ick. So my trick is that you ate something icky. So you ate something icky tells you that you changed 8 to ick. So the idea here is that if you use your polyatomic list, you would find that SO4 is the sulfate polyatomic. So we do not use the prefix hydro. Hydro is only used in binary acids. So what you do when you see that hydrogen is listed first, and we know that we're working with an acid and that acid contains the sulfate polyatomic, this is what we need to substitute out. So we change 8 to ick. Now here's another sub-rule, and I've never really thought about it. And I've done research on why this happens, but there's never really a good explanation, is it's not sulfic acid, it becomes sulfuric. Let me rewrite that. My handwriting's not doing too well right there. Sulfuric acid. So again, it's probably some rule with English that's out of my bounds, and fortunately is out of my bounds. So that's one where it's an exception to the rules, and I don't have a reason why we have that change. But I have more examples, so have no fear. So on the next one, we have the polyatomic NO3. NO3 is the nitrate polyatomic. So when I look at this, I can see that I have hydrogen, so I can recognize that it's an acid. The next thing is I see that NO3 polyatomic, so I have to figure out what is my polyatomic name. It's nitrate. Because it's an oxyacid and it contains an 8 polyatomic, 8 changes to ick, so this becomes nitric, and then the second word is always acid. So in all naming systems, whether it's a binary or oxyacid, acid will always be your second word. That always links the fact that you have a hydrogen cation. We are now not using the prefix hydro because we are not working with a binary acid. Okay? So then the other option, depending on your oxygens that are available, will change the next branch. And these are the ite polyatomics, like sulfite, nitrite. So ite changes to os. And unfortunately, I don't have a trick to keep that. But if you can keep 8 to ick, that can kind of help eliminate that ite changes to os. So same idea. Here I can see hydrogens listed first in my compound. That's my first red flag that it's an acid. The next thing is I recognize I have an oxyacid because oxygen is present. So I need to figure out what my polyatomic is, and that is the sulfite ion. Again, just like before, we do not use the prefix hydro. We get rid of ite and we change it to os. Like the last one, for whatever reason, it's not sulfus acid, but it becomes sulfurous acid. Okay. So here we have HNO2. So I see hydrogen right out of the gate. So I know that it's an acid. So I can add that second word. I have to recognize my polyatomic. NO2 is the nitrite Polyatomic, the ite is what's going to get removed and changed to our new ending of -ose. So this becomes the nitrose. And so we name it nitrous acid. So these are the three branches, and that's one thing this sheet does very well, is it hydrogen plus a what? If it's a halogen, that's basically meaning it's going to be binary because it's going to be hydrogen with a nonmetal. So you have your hydro, fill in the blank with your stem, suffix ic, and acid. Those are binary acids here. Polyatomic ion tells you ate to ic, ite to ose. It shows that acid is the second word, and no prefix, no hydro that's kept with that. Okay, so last part is just a few mixed problems. So the first thing is I would go ahead and pick out anything that is binary. So what are you looking at for binary? It's made out of two elements. The only one I have for you is number 1, HF. So because this is binary, that's going to decide what rules apply. So when I look at my list, either the roadmap or the notes above, the first thing I can see is it needs the prefix hydro. So then I need to add the stem of my nonmetal. So we've been doing like fluorine to fluoride. So that first part is what we're going to keep. And instead of the "ide" ending, it changes to "ic." And like all of them, the second word is acid. So this is hydrofluoric acid. Okay, the rest are oxyacids. And so then the last thing is figuring out what polyatomic they have. If you look here, this is the acetate. Polyatomic, this is the phosphite. And this is the phosphate. So that will decide how I name them. These are not binary, therefore none of these will have the prefix hydro. So then you have to look at your suffix to decide how it will change. 2 and 4 are 8 polyatomics. 8 is going to change to ic. So this is going to become acetic acid. Okay, so I'm going to go ahead and name number 4 then to keep in the same frame of mind. So this becomes, and this is another one that is an exception to the rule, and I wish I had a reason why, but I really don't, is it becomes phosphoric acid. Last one then is we have the ite ending, and ite changes to ose. So pretty much everything's the same as number 4 except our ending because we have a different number of oxygens. So this becomes phosphorous acid. And there we have changed all of them from a formula out to a name. So the last remaining 4 examples is just going in the opposite direction, where a full name is given to you, and then you're going to write a formula. The one thing that you can see is all of them have the word acid. That tells you right away you know your cation. Because it says the word acid, hydrogen must be your cation. You will never have a different cation with an acid. Okay? So then the next thing is, let's look for any that are binary. How would you know that they're binary? The red flag to distinguish binary from oxyacid is the prefix hydro, like we see here in this example 5 and this example 8. So these are only going to be made out of 2 elements. So to figure out what my second element is I have to use the stem here. So I can see it's sulfuric, so I know that's going to flag it as sulfur. Hydroiodic, iodic is going to come from iodine. Because these are binary, that means those are elements off the periodic table, are nonmetals, and so that means you need their charges. Sulfur is a -2, iodine's a -1. So sulfur, I said, was the -2, iodine's the -1. So from there, we're going to cross our charges, just like we've been doing. And I was kind of lazy here, and I didn't write the 1, I just wrote a plus. So when we cross our charges to get our final formula, this becomes H2S, and this just becomes HI, and those are done. The other 2 I know are oxyacids because there's no prefix hydro. So the thing that's going to help me move forward is the ending. These endings, again, I can work in reverse. So what polyatomic did this come from? Because this ends in chloric, this means it came from the chlorate polyatomic. So I need its formula and charge. I would go to my polyatomic list. Here's chlorate. Formula is ClO3. It has a -1 charge. Chlorus, os, came from an ite ending. So this is the chlorite polyatomic. So when I look up my chlorite polyatomic, its formula is ClO2 with a -1. Both cases here, I have a +1, -1, so no new subscripts, no parentheses. So we have HClO3 and HClO2. So like I said, acids are a little bit tricky. The one thing that's nice is there's really not many combinations out there for acids because you're limited to, first of all, always having hydrogen as a cation. And so there's only so many nonmetals it can bond with and so many polyatomics it can bond with. So you have an assignment. You're going to see a few that are redundant from the notes. But like I said, that's partly because there's only so many acids out there. If you need further help, have further questions, please reach out.